Hello, Chemistry 10HH students. This is Mrs. Ullman. We are on video number 14, Atoms, Molecules, and Ions, Part 1. We are in Chapter 2 of your textbook. Here are, actually, no, I guess I didn't put the objectives in. I'm not going to fix it now. Anyway, law of definite proportions. Pause here and write, please. So the law of definite proportion, that just states that a given compound, for example, CO2, is always going to contain the exact same proportion of elements by mass. So for example, in the case of CO2, that will always contain 27.3% carbon and the rest by oxygen. And that just logically makes sense because we're always going to have the same ratio of different types of atoms. And on average, atoms will have the same mass as one another. When I say on average, that means that we are accounting for isotopes. Some of you are probably wondering, of course, that there are different isotopes and that does affect the mass. We'll talk more about that later. But in general, this is true. Pause here. So Dalton's atomic theory, which is a little bit different than the atomic theory we talked about in our last chapter, is a little bit more general, not really talking about sort of quantum phenomena. This is stuff that you've probably heard before. So the first, all matter is made up of tiny particles called atoms. The atoms of a given element are identical. That is actually not 100% true. They all have the same number of protons, but they can actually differ in the number of neutrons. Chemical compounds form when atoms of different elements combine, and chemical reactions involve a rearrangement of atoms, but not a creation or a destruction of atoms. Pause here. So this you should already know. If you haven't already seen the letters AMU, that stands for atomic mass unit. It is just in a unit that is extremely small. It's approximately 10 to the negative 27th kilograms, so a really small amount. And we do use these symbols as standard symbols, meaning that if you're going to abbreviate proton, it has to be P+, neutron has to be N0, and electrons has to be E-. Electrons do have a mass, but they are, it's such a small mass that it's essentially massless. So the mass of an electron, I think it's like 9.109 times 10 to the negative 31 kilograms, compared to something on the order of magnitude of 10 to the negative 27th kilograms. That's about one. That's a very large difference between the two, about 1/10,000th of an AMU. Pause here. So we've looked at atomic numbers before when we were doing electron configurations. We use them to determine the number of electrons, and you can do that whenever something is neutral. It's just the number of protons in an atom's nucleus, and whatever that number is, that determines the identity of the atom. Pause here. And the mass number is the sum of the number of protons and neutrons. I would add here that that is within a specific isotope. So the number that is on the periodic table, the larger number that's on the bottom, that is actually not the mass number. That is the average mass, which is the weighted average of the mass numbers of all of the different isotopes. So here, when we talk about the mass number, we're talking about a specific isotope. Pause here. Okay, full atomic symbols can really just convey what's going on in a specific isotope of an atom. So it has to be a specific one. It is not all of them. So A is the mass number, just the protons plus neutrons. Z is the atomic number. X is the symbol. So for example, 12,6 carbon, that is carbon with 6 protons, 6 neutrons, and 6 electrons. Pause here. Okay, so carbon always has 6 protons. I know that's from the periodic table. This is saying that the mass number is 13, so we're just going to put 13 for the mass number, and the symbol is C. So this has to have 7 neutrons because 6 plus X is equal to 13. Okay, and that is the end of the video. I don't know why I put the objectives at the end. I probably won't do that again. Thank you so much for watching, and have a good night.